So now we're going to look at phase changes, um, which includes looking at phase diagrams and these um, properties as they relate to solutions. So a phase is a homogeneous part of a system in contact with other parts of the system, but separated from them by a well-defined boundary. So what does that mean? For example, in this glass that we have here with a summer drink in it, we have a liquid phase, and we can say this is water, and we have a solid phase, which are the ice cubes that are in that water. There also is a gaseous phase, so there, if this is water, we're going to have some gaseous water molecules in the atmosphere right above the surface of that water. So phase changes obviously are going to be changing from solid to liquid, liquid to gas, or solid to gases, where we can associate a graph with that with respect to kinetic energy, which is depicted on the right or the left side of this panel. But we can go from solids to liquids, liquids to solid. So these are reversible processes. Liquid to a gas, gas to a liquid. So evaporation, condensation. This would be melting. This would be freezing. And we've, I believe, defined this, but if we convert directly from a solid to a gas, that is called sublimation. And if we convert from a solid to, or sorry, a gas to a solid, that is called deposition. Okay. So number of molecules in a particular phase can be related to chemical energy or kinetic energy, excuse me. So this is number of molecules associated with T1. And if we look at T2, which is greater than T1, we're going to have fewer molecules in that particular phase. So as we increase temperature, we have a conversion from one phase to another. Also, in nature, if you take 1062, this will be discussed in more detail. There's a tendency to go spontaneously from greatest order to least order. Sorry, I didn't know that around there. Okay, so defining some of the properties associated with phase changes. We need to define the equilibrium vapor pressure. So this is the vapor pressure measured when a dynamic equilibrium exists between, for example, in this case, condensation and evaporation. So let's say that we have a glass or beaker with water sitting on a bench top. Evaporation begins, and once it reaches a plateau or a certain point in time, then condensation also begins. So, and then at some point, they reach the same level. So the forward and the reverse processes are equal, and at that point, we say a dynamic equilibrium has been established. So we can look at this for liquid vaporizing to gaseous water. And once again, at that dynamic equilibrium, the rate of condensation is going to equal the rate of evaporation. So how do we measure the vapor pressure of a liquid? And this is a diagram of that apparatus that is utilized. We have a container that's capped, empty space above the liquid in this container. And there's a side arm. We've seen, well, actually, sorry, we haven't seen this yet because we haven't talked about gas laws yet. But what we have in here is a column of mercury. And then this is a vacuum here. So even with this empty space, the height of the mercury in this column is equal. Okay. Once these liquid molecules begin escaping from the surface and filling up the space above that liquid in the form of vapor, they will eventually apply a pressure to that column of mercury. And at some point we can measure that, and that measurement the vapor pressure will be equal to the difference in height. So this vapor pressure will be given in millimeters of mercury. So before evaporation, at equilibrium, gives us the vapor pressure. Vapor pressures have been determined experimentally for a number of substances. And when we discuss gas laws, we'll see that we'll look at vapor pressures of water quite a bit because that varies by temperature, of course. So what is the boiling point of a liquid? This is the temperature at which the equilibrium vapor pressure of a liquid is equal to the external pressure. So that vapor pressure above the liquid is equal to the atmospheric pressure. Okay. So boiling point can vary. And I think we all know that. Boiling points in Minnesota, at least for water, let's say as an example, are going to be different than the boiling point of water in Denver, Colorado, which is at a higher altitude. So that will affect the boiling point. There are what we call normal boiling points. So this has a criteria attached to it, and this is the temperature at which a liquid boils when the external pressure is 1 atmosphere. So we could say typically the boiling point of water in Minnesota is 100, assuming an atmospheric pressure of 1 atmosphere. We know the atmospheric pressure in Denver is lower, so that would affect its boiling point. But the normal boiling point is at 1 atmosphere of pressure. And here we can compare some boiling points. They also, in this table, is the delta heat of vaporization, and that's the energy that is either, well, depends upon whether we're vaporizing or condensing, the reverse processes, but this is for vaporization. If we look at, let's compare methane, for example, because we've looked at that before. Boiling point, negative 164 degrees Celsius, compared to water at 100 degrees Celsius. Delta heats of vaporization also reflect that difference in those physical properties. Why is this? We have just discussed why, actually. And that is related to intermolecular forces, or their IMFs. We know methane is a non-polar molecule. Thus, it only has London dispersion forces, where water is a polar molecule and is capable of hydrogen bonding. Critical temperature. And we're introducing all these terms so when we discuss phase diagrams, we'll be able to relate the meaning of these to the phase diagram as well. So critical temperature, which is represented by T sub C, is the temperature above which a gas may not be made to liquefy, no matter how great the pressure applied. Okay? So there is a temperature at which, if we go higher, it doesn't matter how much pressure we apply, we cannot liquefy that gas. With it, there is also attached a critical pressure, or coupled to it, I should say, the P sub C. So this is the minimum pressure that must be applied to bring about the liquefaction at the critical temperature. So take a look here at water, again, our unusual molecule that compared to other molecules of similar size, it has much higher boiling point, melting point, and of course, with respect to IMFs, it has all three, the capability to hydrogen bond. But its critical temperature, 374 degrees Celsius, and the critical pressure, 219. So the critical temperature is pretty high and requires a considerable amount of pressure in order to liquefy gaseous water molecules. So beyond this temperature, water cannot be liquefied. Where is methane? So I was going to tend to make the comparison there. Methane's critical temperature, minus 83. Critical pressure, 45.6. So a significant difference. And these two molecules are of similar size, molar mass, yet they have distinctly different IMFs and strengths of IMFs. Oh, we could compare one more here. Let's compare carbon dioxide. So methane again is nonpolar. Carbon dioxide is also nonpolar. So let's compare these two nonpolar molecules, both of which would have only dispersion forces. So again, methane, minus 183 critical temperature. Carbon dioxide is 31 degrees. So much higher. Why is that? They both only have dispersion forces. So it must be related to size and mass. And methane's molar mass is around 16. Sorry, I don't write well with a mouse. Of course, we know water's around 18.02 to be exact. And CO2 is about 44. So, a little over twice the molar mass of methane, and again we see the distinct difference in those critical temperatures here. So this is just a slide that shows samples of sulfur hexafluoride. And in the first panel here, it is completely in the liquid state. And our temperature is less than the critical temperature. So it's a liquid. In the second panel, it is completely gaseous or gas. And, whoops, sorry, hit the wrong thing. Its temperature now is greater than the critical temperature. So at this temperature, it cannot be liquefied regardless of what the pressure is. In the next panel, our temperature is at approximately the critical temperature. And we have essentially a mixture of, so we have a little bit of gas, a little bit of liquid, maybe more gaseous or vapor than the liquid. So we have this foggy condensation of that vapor. And then finally, when we go back, so actually what's happened here is we've cooled from above the critical temperature to about the critical temperature. So this gas is starting to condense and liquefy again. And finally, in the last panel here, our temperature is less than the critical temperature, and the liquid phase starts reappearing. All right, so melting and freezing. So this is going to be an equilibrium or a process where we're either converting a solid to a liquid or a liquid to solid with respect to changing phases of water. And this is called, the temperature at which this occurs, I should say, is called the melting point or the freezing point of the liquid. And it is the temperature at which the solid and liquid coexist in equilibrium. And for water, that is 0 degrees Celsius. Okay. Boiling point, it would be the same. We could apply it similarly. That is the temperature at which we either vaporize liquid water or we condense gaseous or water vapor. This is what's called a heating curve, and after this video I'll be making another, and we'll work with solving some practice problems and drawing heating curves and taking a look at some phase diagrams, example type problems. But at any rate, what we have here, let's say this is minus 20 degrees Celsius. And let's say we've got a water sample. So we have ice at negative 20 degrees Celsius. And we are increasing temperature, and this is time is on our x-axis. So as we start warming that solid ice, it is absorbing heat. So this is, I didn't do that very well. From this point up to A, we are warming. And once again, I don't do well with writing with a mouse. When we hit 0 degrees Celsius, the melting point of water at this point, at this point in time, at A, we have a solid. As time goes on and we maintain that temperature at 0, we will reach a point of equilibrium. But if we continue maintaining that temperature, after a certain amount of time, the solid will be completely converted to a liquid. And then we can increase that temperature again. So in this, from point B to point C, we are warming our water. Once we hit point C, which, dealing with our water, boiling point 100 degrees Celsius, it will be completely liquid here, and by the time we get to point D, it will be gaseous. And midway through, we'll have that equilibrium state, a mixture of both liquid and vapor. And then we could continue heating that vapor. Okay. So melting and freezing occurs at one temperature. Vaporizing and condensing occurs at one temperature. We're still absorbing heat, or we've got that input of heat, but that energy is not being used to increase the temperature of the sample, but is contributing the energy required for that phase change to occur. All right, the last phase change, of course, is sublimation and deposition. We have used carbon dioxide as an example of that in the past, but your text uses water, converting from a solid directly to a gaseous state. This is associated with what is called the molar heat of sublimation. So remember, we have a delta H of fusion. We have a delta H of vaporization. So there's also a delta H associated with the sublimation process. And this, however, molar implies a mole is involved here. And so this is the energy required to sublime 1 mole of a solid. And this is something we can actually use Hess's law to explain sublimation, or calculate sublimation. And the delta H of sublimation then would be the sum of the delta H of fusion plus the delta H of vaporization. Okay, an application of Hess's law. Okay, so phase diagrams. These are used to predict changes in melting points and boiling points of substances as a result of changing temperatures and pressures, or when temperature is constant and we have changes in pressure. So basically, the phase diagram summarizes the condition at which a substance exists as a solid, liquid, or gas. Okay? So we're going to look at the details of this phase diagram of water. Of course, we know the melting point is 0 degrees Celsius and the boiling point is 100 degrees Celsius. And the boiling point is 100 degrees Celsius at 1 atmosphere. And of course, the associated freezing point is also at 1 atmosphere. Okay. So we have these curves in our graph. Temperature across the bottom, of course, pressure on the side, the y-axis. These lines represent the equilibrium between different phases. So this line represents the equilibrium between solid and vapor. This part of the curve between solid and liquid, and this the equilibrium between liquid and vapor. at a particular temperature and pressure. Within these regions, we have all solid, all liquid, all vapor. There is a point at which these three lines intersect, and that is called the triple point. And at this point, all three phases are at equilibrium with one another. Okay. So intermolecular forces between molecules or atoms are going to govern whether a substance exists as a solid, liquid, or a gas. And with increased temperature, a substance is more likely to be found in the liquid or gaseous state. But pressure also plays a role. So this is where the attributes of these phase diagrams help us predict whether a substance will be a solid, liquid, or vapor at a particular temperature and pressure. Consider with the fact that we just defined critical temperature and critical pressures for water a few slides ago, you see on this phase diagram, we couldn't possibly see where that critical temperature is. This is 100 degrees. The critical temperature of water is 374, so it's way, way out here. And this is 1 atmosphere. And the critical pressure, I think, was 219 atmospheres. So that point is way off this graph. Anyway, say I want to know whether water is going to be a solid, liquid, or gas at 0.06 atmospheres. I find that point at a particular temperature. Well, actually, this is the triple point. Never mind. We'll do this on a different slide. So the triple point occurs at 0.006 atmospheres and 0.01 degrees Celsius. Sorry, I was jumping ahead of myself there. But we'll do that on this next slide. So, increasing the pressure affects melting point of ice and the boiling point of water. And so, as I said, we can use these phase diagrams to predict whether something is going to be solid, liquid, or vapor, but we can also use them to visualize or determine the effect pressure has on these physical properties. So in the first panel, let's see, we just saw the normal freezing point, 0 degrees Celsius, the normal, actually this is the normal, sorry. So normal, and how we're going to use this to determine changes in melting points and boiling points. So what happens if we increase a pressure above 1 atmosphere? Okay. So here, all we're going to do is, determine the boiling point, draw a line over to the equilibrium line between liquid and vapor and down to the x-axis. And that will give us the new boiling point, which is increased. This is the 100-degree boiling point right here, normal boiling point, or the boiling point at 1 atmosphere. So when we increase pressure, we increase the boiling point. But what happens to the melting point? So we go over to the equilibrium line between solid and liquid and down to our x-axis. And we find that when we increase the pressure, we decrease the melting point. What happens if we lower the pressure? Let's say we've got, let's say this is 0.5 atmospheres, for example. Yeah, we can do that. What is our new boiling point? Significantly less than the 100 degrees Celsius of the normal boiling point. And so we have decreased. When we decrease pressure, we're going to decrease the boiling point. And I think you would predict a decrease in pressure is going to increase the melting point, and it does. So our melting point increased here. So you should be able to use a phase diagram to predict these changes in boiling points and melting points when we change pressures. One final slide, a phase diagram of carbon dioxide, which of course has different physical properties than water. We see its triple point. It occurs at 5.2 atmospheres and -50 degrees Celsius, so much higher pressure. Water's pressure at the triple point is 0.006 atmospheres. The curves are different, so the curves are going to be unique depending upon what the substance is. And we can also see, of course, at 1 atmosphere that CO2 is a vapor at 1 atmosphere. And these are the temperatures. So, different substance, different phase diagram, but same ability to predict phases.